Hello everyone. On today's video, I'm going to show you how to run a TOCSY experiment or a total correlation spectroscopy experiment. And here I'm actually showing the difference between TOCSY and COSY. COSY means correlation spectroscopy. So COSY gives me information of the hydrogens that are directly coupled to each other. So for example, I have a J coupling, scalar coupling between these two hydrogens, so I will see a correlation between these two hydrogens. Also, I will observe like a correlation between this hydrogen and this one, and also between this one and this one. But if I don't have any kind of coupling, for example, if the J coupling between this one, this hydrogen and this one is equal to 0, I won't see any correlation on the COSY spectrum. However, on the TOCSY experiment, the TOCSY gives me an extended information. So as long as I have coupling, for example, between this hydrogen and this one and this one and this one, I can transmit the information from this guy to this guy and from this guy to this guy, even though the coupling from this one and this one is equal to 0, this one is equal with this one is also equal to 0. So TOCSY gives me the information of my spin system. So I know that's this hydrogen, this, and this, they belong to the same spin system. Because for example, this, like the coupling here is 0, so I won't have like any transmission of information from one system, one spin system to the other spin system. Okay, so on this slide here, like this one, because I have a comparison between COSY and a TOCSY experiment, and here's the assignment. So I have like H2 here, okay, H2, H3, 4 and 5, and 6 and 6 prime here. So look at this on the COSY. So the red arrows here shows the COSY correlation, same as here. The red arrows are showing the COSY correlations. So for example, H2, if I look at H2, my H2 is here. I see a correlation. So first of all, like I see a diagonal on both spectrum. So this is just like just chemical shift, right? So this, if I look at the diagonal of H2, I see a correlation of H2 with itself. It's just a chemical shift. But if I come to the diagonal and I go back, like I see a correlation here and here, exactly the same thing, right? And if I go back to the diagonal here, like I see a square, and this square gives me the information, like if I follow either like in the vertical or in the like on the horizontal, I see information, for example, a correlation between like H2 and H3, which means that H2 and H3 are directly coupled to each other. On H3, if I follow here, I also see a correlation with H4, right? Which means that H3 is also coupled to H4. But look how different is the information that I have on the TOCSY experiment. So on the TOCSY, I not only see a correlation between H2 and H3, but I also see a correlation, for example, between H2 and H4, even though H2 and H4 are not directly coupled to each other. So I see this correlation between H2 and H4, right? Because H2 is coupled to H3 and H3 is coupled to H4. So as H2 transmit the information to H3, H3 is able to transmit the information to H4. It's like a gossip. So imagine that the hydrogen says like, for example, hydrogen 2 says to hydrogen 3. So this is my chemical shift. And how this information is transmitted? It's transmitted because there is a J coupling between H2 and H3. And then H3 tells H4, like, okay, this is my information and also the information of H2. And this is also like it's allowed because I have a coupling between H3 and H4. Okay. So I'm gonna now move on to the top spin. So I share this, and I will share the top spin so we can see the parameters and a real, like more like real life spectrum. So this is the spectrum of a peptide, and it's a really good one. We have a lot of resolution. So another important thing is, I don't know if you guys observed, but the information that I have on this side is the same information that I have on the other side. So this is a symmetrical experiment. So if I look here, for example, I'll see that I have this is my pulse sequence. Okay, so my pulse sequence, the mixing time block is performed using gypsy block, a gypsy block. Or DIPSY2 actually. ES means excitation sculpting, so it's for water suppression. I have gradient pulses, and it's a phase-sensitive experiment. So the acquisition mode states the PPI, and this experiment was acquired with 2 K points on F2 on the direct dimension and 1 K point in the indirect dimension. So I have a lot of resolution. This is because I have a peptide and I need a lot of resolution on the indirect dimension. This experiment was acquired with 16 scans, okay? And you see like the spectral width, like it's symmetrical. And I mentioned that this spectrum is like a symmetrical spectrum. So I have to acquire with the same sweep width or spectral width on both dimensions. Also the same transmitter frequency on both dimensions. So, and I put like my transmitter frequency on water peak because I need water suppression, because this experiment is performing in water D2O 10%. So this is like my mixing time. So on TOCSY, my mixing time is on it's D9. Okay, it's my mixing times here, TOCSY mixing time. And usually like you use 20 milliseconds when you want to like the information to be more restricted to the closest correlations, like when you have like want to observe like correlations between the hydrogens like directly coupled, or at least like, you know, like the more close in the spin system. And you use like 8 milliseconds when you want this information to be extended to longer to the hydrogens that are more distant in the spin system. Of course you won't like use like more than 8 milliseconds, starts to have like lots of relaxation, because during the transmission of information, my magnetization is on the transverse plane. So that's the usual range, like 20 to 80 milliseconds. So use like and most of the time you acquire like you can acquire either one, like 80 milliseconds, or 2 experiments like 20 milliseconds and 8 milliseconds. So you can pretty much discriminate which ones are close and which one are more distant in the spin system. So this experiment also like use excitation sculpting. So this is the length of my selective pulse on water, 2 milliseconds. I'm just using the one recommended here. And this is the power pulse that goes with the selective pulse on water. So it's just it's 24. In this case, I'm using about like 24.5 dB. So it's just like, you see, like milliwatts. So I have like a long pulse here. So I use a really tiny amount or a weak power because I want to make my pulse selective. Okay, so this is adjusted on GS. When you run GS, you can adjust SBDB1, same as we adjusted on the ZGESGP experiment. Actually, you can do like the adjustment on the 1D and then just use this information for the 2D. This pulse was also like calibrated. So, and for calibration, we use pulse call, same as mentioned on the other videos. So that's what I wanted to show you on this video. Remember to respect the number of scans for phase cycling. So multiples of 8 in this case. And I see you guys on my next video. And I hope that you can run like a really nice TOCSY experiment from now on.